Play on music, that was lovely. Made everyone very quiet, that's good. What a full house we have tonight. Welcome everybody to the 5th of this year's public speaker series, Science Fiction by Wiradjuri Nation. It's upon their ancestral land that the Academy of Science has been built. As we share our knowledge, teaching, learning and research practices, may we also pay respect to the knowledge embedded forever within Aboriginal custodianship of this country. I also need to mention that this is Mr. Lights. He now heads up the Non-Linear Physics Centre at the ANU. So please join me in welcoming Yuri and let's hear what he has to say about getting us all invisible.
General audience, because you know scientists do not speak a normal language. We speak jargon, and it's very hard to explain very often people what they're really doing. I was asked to talk about novels, but this is probably one of the most famous novel about invisibility, and basically comes from the real knowledge. That's sentence which I found and basically explains the idea why it was fictum or jargon. But just want to say that it was some sense in creating idea of the invisibility man in that time. But later on, of course, was many different stories written exploring this invisibility idea. This is from 61, Lynn Kirby. And we have many more than there. So this lady who becomes invisible, she achieves this feats by bending all wavelength of light in the vicinity around herself. That's very close to the idea I'm going to talk today about. So you see, when in 61, it was some knowledge or some understanding how to make things invisible, or just try to hold lights in some volume. Okay, what happened next? Of course, you know very well all the stories about Harry Potter, but unfortunately, we don't have idea how Harry Potter created his invisibility cloak. It was not explained by Rowling, and I was not able to find any clue. So that's already magic. When you can explain it, that's basically magic. Light to propagate through, so basically don't change much of picture, but it's not real. It does not allow you to see rays. And there's another story. I just will show you. So you basically see through the object, and you believe that you created a substance which allow exactly to realize Wells' idea of making refractive index, the same like subject. But it's not true, because it's actually done in a completely different fashion. So basically we have an object, we have a camera which actually screens the entire space behind the camera, and then it reproduces on the picture, and then we see actually that what happens behind the object, which actually not true because object is not transparent. So this is not what I'm going to talk about. I will talk about something else. This camouflage has many drawbacks, bad points and good points. Of course, bad points, it works in the plane of camera. It shows some reflection, of course, not dynamics, static, so it's not what we want to see from invisibility. Of course, good points, that's actually we can show it, you know, many movies and basically say that we achieve invisibility. However, if you look carefully, wow, that's we forgot to remove tripod from that image. Of course, this is kind of cheating, but not what we are talking about when we understand invisibility. Okay, before starting the scientific part, explaining how we, in principle, we may do something what we may associate with invisibility, I need to come to scientific terms and explain a bit of this jargon we are using, explain some notions. So what we understand by light? Light actually is not that global notion, even we like to say about light, like something absolutely globalistic. So it's a part of electromagnetic waves, so only small part, because usually we understand in science light means visible light, exactly what we can see by our eyes. So of course we have ultraviolet, infrared, so it's even around visible, we have a kind of broad spectrum. But in general, electromagnetic waves cover the entirely broad spectrum from, of course, gamma rays, which you probably don't see, but X-rays, which we don't see by field when we go to make X-ray screening, up to radio waves, which you obviously understand how they work because you watch TV or you listen to radio. So this is all electromagnetic waves. So basically light is a small portion of that. When we talk about cloaking, we basically talk about cloaking from electromagnetic waves in different wavelength regions. So we can do it here, microwave is easy, and because it's large, we can do invisible. Of course, people want invisibility invisible. That's why invisibility is used as a term. Okay, now, of course, we see that visible part, and that's why it's a bit difficult, but let's go to general knowledge again and see what light does when it propagates and interacts with object. When we see any object and shine light, so basically we have reflections, transmission. Invisibility means that light goes through the object entirely, so it does not feel and doesn't show object. So what else we can do? Obviously, with light, we can absorb light, and that's absorbers is a kind of branch of physics which related to solar cells to absorb and transform light, sunlight. That's what with absorption, we have light coming, light interacts with the internal structure of material, and energy is somehow lost in the vibrations of these electrons. We can have reflection. That's obviously what happens when you see objects. We see objects because light interact and reflect to our eyes. That's basically reflections which allows you to see the object. But also we want to have transmission. If density of material is not strong enough, like usual glass, so we see through the light, through the material, and that's exactly how this initial the invisibility man concept was created. We assume that we can drink something, we can make ourselves like glass and make transparent. But it's not easy because we consist of different type of materials. Okay, what happens if you have any object and we scatter light? Obviously, light goes through when it does not interact with object, and of course it's reflected, go around the object. That's what we understand in science, creating invisibility cloaking. So we surround the object by some cloak or shield, whatever, and then try to bend rays around them to make exactly looking as similar to rays which do not interact with objects. So basically we remove reflections. Question is, if we can do it, how to make them. So to make this, we need actually to go to the understanding of laws of bending of light. So we need to learn to bend light. And how we can bend light? Of course, if you look at textbooks, we know refraction. Refraction, it's most scientific terms. It's explained how light interacts with interfaces, with the boundaries between two different materials. So let's say one is air, the second is glass, so light, when propagate and penetrate into glass, it bends. Of course, bending depends on somehow density of that material. Air is not dense, materials, solids are denser, so denser the material, slower light propagate. So this means that if I have that picture, basically this picture means that I refract light, just shift it. This means that light, when penetrates in water, it bends, and this image of your pencil which you see is bended or shifted. Here, that's the simplest example. Again, so this is all known and how we can actually describe it. We describe it by this term refractive index. Refractive index, index of refraction or ability to refract light. How to understand that? Of course, we go to elementary physics. You know that all solids, all materials consist of molecules, atoms, and solids, they consist of density-packed molecules, but we don't know that. In order to understand the structure, you need some specific devices to actually look inside of the structure. If I have something like that, I do not care and I don't see what is inside. And it's normal situation because size of these creatures is very small. So what's actually happening? We see some materials like that. We average, somehow average, we care about this density of internal arrangement, which can be described by simple refractive index notion. Sorry, losing a bit voice. Okay, so how light interacts with interface? It's interacts according to Snell's law. It's very old physics. And school textbooks, basically light propagate like that, as you saw from my previous pictures. And of course, we try to characterize it. What about this? It looks a bit unusual, right? If you go to textbook, obviously, until recently, you were not able to find it. So it's somehow bending in the wrong way. We call this, I'm going a bit ahead, we call it negative refraction, because normal refraction positive, this is negative. The question is, what is the consequence of that? Consequence of that you go to this famous formula established by Snellius long time ago, and we discover that if you try to apply that formula, we need to assume that our refractive index is negative. Immediately question is, if it's something that would characterize density of material, it's crazy. So all Maxwell equations depend on n squared. So Maxwell and everybody else who works with Maxwell equation, we don't care of taking square root from n squared, but if you take square root from n squared, you have two options, plus and minus. And this is the case when you should take minus. Okay, we go ahead and we ask ourselves if we can imagine that in general we can have this negative refraction. Do we need any nice word? You know, it's a very big success of any scientific project of article is a title. As soon as you invent something catchy, you know, immediately you'll get success. So meta in Greek means beyond. So it actually has sense because beyond all properties, beyond materials, metamaterials means materials which something beyond what nature gives us. And negative refraction, it's by definition, all metamaterials have negative diffraction. And imagine that instead of that normal glass, I have left this metamaterial water. So it will bend this pencil in a different way. I give you another example, you know, it also can be reproduced at home, but not with, of course, negative index water, but with normal water. You take a cup, and it's actually, I think it's school science, physics. You put a coin and put your eyes to hide the coin, and then fill the glass with water. You will see the coin. Why? Because of this refraction, you will see the coin elevated. If I would have this metamaterial water, I will see it flying on the water, but no water yet with negative refraction. At least not known at the moment. So what are metamaterials? I will give you definition one by one. So first is metamaterials is the structures, which are composite structures, consisting of small elements, similar to what nature does with molecules and atoms. We do with our structures. I will come again to the definition, but just first definition is that it's a composite materials which consist in some small creatures. Don't understand now what is that. And in average, we change refractive index in the way we want. or we put properties of that structure, average properties, in the way we want. Of course, we come to some images, but negative index, as I said, Maxwell equation allows you to simulate, to reproduce numerically anything. And as soon as n squared, it becomes positive, and it allows negative n. So this example of refraction, which I show, this is normal refraction. This is a Gaussian beam, so localized shape beam which propagates and interacts glass and air. Now this comes from glass and goes to air. This is an example of negative refraction. I repeated again, of waves, which are called backward waves. Any kind of wave is characterized by velocity. We call group velocity is a group velocity which describe propagation of beam or negatively. I hope I try to put some physical terms into that, but at least you should remember these two pictures, so it's bending in a different way. Okay, coming now to more realistic definition of metamaterials, I show you this picture. So 100 nanometers, 50 nanometers, it's more reasonable, 300 nanometers, so hundreds of nanometers. So we made them. This example of this, what we're making, this is horseshoe type of structures. I will briefly mention why is that, because we want, this is made of metals, we want some current oscillating in the structures. If current oscillating, change magnetic response of these materials. And this is very important because we can get materials which are non-magnetic to be magnetic. So magnetism, that's actually from scientific publications, everything real. So real, I mean man-made. So different examples. So what we see in that pictures, these metamaterials have some structure, so we consist of something. This something has some specific purpose why it was done, to enhance polarization, enhance response, magnetic, electric. These are examples. This is even more sophisticated, but it's also metamaterial. So it's a metal, dielectric metal multi-stacks with the holes. Holes, we need to control magnetic response. Stripes, we need to control electric response. That's probably too much. This is interesting image. When all this negative refraction appears, several big companies actually said, wow, what this scientist doing, something crazy. And Boeing Corporation created a special team to verify this nonsense publication, as we call it initially. And they created a piece of perfect metamaterials, we call it Boeing Cube, and verified that everything actually real, and negative refraction and all magnetic response can be engineered. Okay, coming back to invisibility, I just trying to give a line of all these presentations which will not under my talk. So what we want to do, we want to create this region which will do something with rays, with our light waves, which will propagate and reflect from objects. We want to bend them in a way like that. And this is shown what is actually happening there. So if you bend them like that, so if you see the object, you don't see reflections, you don't see shadows from object because rays do not actually interact with the object because objects are hidden in that region. To do that, we need to do something with space. We need to do with that region. We need to create it. How we can create it? We made this region from materials which consist in the small elements and change properties of that material. There is no way to do it with natural materials. Why? Because we need to simultaneously change electric and magnetic response. Electromagnetic waves have two hands, electric and magnetics, and we need to manipulate these properties simultaneously. That's impossible with normal materials. That's why metamaterials allow to do that. So instead of that interactions, we bend rays, or we may even create shield around which will change properties. For example, we start from one color and get another color. So basically kind of camouflage, but it's a different type of camouflage. Okay, that's what we want to do. I mean, in some sense, what we are trying to do, we put a point, and now we expand this point to the circle. It's called conformal transformation, so we are transforming space. transforming material space by means that we create kind of regions which will open holes there, but of course changing properties around the holes to bend lights. So hole ideally should not have any field penetrated inside, and then of course we may hide object inside of that hole. Of course, if you talk to military people, they won't immediately hide tank or airplane, but you can imagine how big you should get that type of environment to hide the tank. Anyway, another way, what we can also do, just look at this very simple cartoon. So if you created this shield or this area, cloaking area, so basically, and we try to look through it, so light which is reflected from our carrot will come to our eyes, but light which go from apple will not be seen, so basically we see only carrot, will not see apple. Ideally, we should have this three-dimensional type of cloaking, so cloaking object from all sides. Question is, why I'm talking about that? Of course, I'm talking because that was created. That was created already some years ago. It was done in a group of my good friend David Smith in University of California, San Diego. He now moved to Duke. And that's the first cloak. It consists of stripes. You see, these stripes has some structures. It works from microwaves because structure is large. So these are meta atoms, and these are stripes. They have varying properties. When you vary from layer to layer, you vary across the domain, and you're allowed to bend these rays. How it works? So if you know that shield, know this area, you see that there is a strong reflection. We send plane wave with plane front, and there is a big shadow created behind that object. Now we put that layered structure, and of course intensity drops, but phase is almost plane, so basically shadow disappears. Intensity of light drops, but shadow disappears. Up, it should be simulation coming, sorry. Yeah, you see how it's happening? In reality, of course, field penetrate inside, some field, but basically it's somehow bends this object and you can place anything inside that. When we started to repeat, or we invented some puzzle clocks, initially we were very excited about that. That happens already some time ago. Our media was so much excited that not one, but all my guys actually very much embarrassed reading like even Harry Potter magic, whatever. You know, I think the only what is true, Australian joined race for invisibility. That's probably true. The rest was so exaggerated by media that we somehow slowed down our activities in that direction, because when you're dealing with media, you know, you should be very careful, because we really want to present something what they like, what not really happening in science. So we created a few clocks, and created clocks which allows you to mimic reflection from surface. But I tried to tell you what is the main problem to make invisibility clocks for visible light, for our light which used in our normal life. Sorry. So this region of visible light is actually relatively small, 380 nanometers, 780 nanometers. I told you that in the concept of metamaterials, we should see properties like average, somehow shadowed by, because we're using the very long wavelength and very small structures. Our waves do not see what this material is made of. But if our wavelength is few hundred nanometers, then basically structure should have 10 nanometers, 20 nanometer size. It's extremely hard to make. Only recently, people were able to fabricate that. There's nanotechnology as a science, or nanofabrication facilities. That's one of the examples. You see that there's a small pyramids from silicon, and density of pyramids is different. You see here, rarefied, more denser. And this is imitation of so-called carpet cloak. Carpet cloak is a cloak which allows you to mimic reflections from flat surface. This is region where we change refractive index, and this arrays. So in reality, reflections should be very strange in different directions because they reflect from this object. But if you put this head or cloak, so cloak will bend rays and will direct them exactly along the trajectories as we reflected. As we reflected from the surface. Anyway, good things. Sorry. Yeah. Good things that, of course, we can actually make it real and check our theory. And bad points, of course, this does not work for all wavelengths. Works in a plane. This is a real image of that clock. So you can hide object here, and that's a clock in area. And only works for one wavelength, so very narrow bandwidths. But of course, easy to make. So what was I telling you about the invisibility and different realizations, but what's really happening? So what we need and what really achieved. I just summarized one slide here, like a steps to success. And first step, of course, I shown you that we can immediately do, using the concept of metamaterials, this invisibility for one wavelength in a plane. It requires some patterns, and we can easy to make for microwaves, for mid-infrared, more difficult to make for optics, but also possible. Invisibility for all wavelength also can be done for much broader, because that scopic cloak actually works for not for single wavelength, for broader wavelength band. But it requires some patterning, again, concept of metamaterials. But again, where is our science fiction goes? Of course, science fiction wants three-dimensional clocking. From all wavelength, from all sides, this is of course impossible. The initial recipe given by Wells in his novel is correct, but it can't be realized. We can't make our body exactly with refractive index of air, because we consist of different densities of materials, and we can't just drink simple liquid. So this is still, and solution in principle still not clear. There are many propositions, some theoretical suggestions, but what is most important, and this is probably first message from my talk today, as my friend and colleague David Smith says that we already have everything in principle to build cloak. The problem, we don't know how, but the knowledge is there. The knowledge is there, the concepts are there, so we can use them. So what else we can do? I just included a few more comments, even I'm already out of prescribed times, but I think it will be useful. So what's happening now? People started to think about what would be effect on visibility. This is from Neuroscience Institute, which actually created a kind of program which allows you do not see yourself, be transparent. So you wear this equipment and you don't see yourself, you don't see body. And then somehow it's human being neuroscience studies which shows that you can create, if you affected from outside and you see some kind of similar actions on the distance, you create illusion of yourself on a distance. So there are many interesting issues about that to actually understand what happens to the person who become invisible. This is very recent studies, actually, published in scientific reports. The real recent breakthrough that happens, which happened already, it was just from June. People make a flexible surface of performance of them, and few percent improvement gives you a lot of money. So that's a big project we have in Germany. This is not for distribution. I guess we already have patents. We are working on meta surfaces. This is kind of two-dimensional version of metamaterials. So this example of them. So this is like a lattice of this of disk or more sophisticated structures. So these metasurfaces are extremely useful for replacing a lot of bulky optics in our laboratories or different type of. Comes from MRI machine. Of course, created new MRI machine is very complicated. So that's why basically what they tell us, we try to use what we have already and try to improve performance of that. This is some results which are now under review in Nature. So imaging of different type of fish, not human, we need the permission to deal with humans. But what is important is that we can do it much faster. I didn't realize that particularly if you improve speed of scanning in science, it takes a long time. What is important at that meeting, it was half a day devoted to technological presentations from people from companies. Many of these companies are just a generation of intellectual venture capitals, which several years ago was supported by Bill Gates with a lot of investment. But of course, majority of these activities, this is in microwaves, radio waves, improving antennas, improving how the communication devices, for example, making charges. I just come with my mobile, put it there, and he's got charge at the end of my lecture. That's ideas around company developments. And as very, very end, just mentioned that this year is a year of light, was announced by United Nations. There are many activities around the country. One of the announcements was in distributed room when you had some snacks. Will be in September. So a lot of activities associated with promoting of light with the attractive concept of physics and the attractive concept for application. Thanks for your attention.
That's probably the most mesmerising physics lecture I've been to in about 45 years, I think. Wonderful. We can open the floor to questions now if you have any. There will be a test, of course, at the end after that, so we'll be getting your results in later on. Are there any questions for Yuri, or should I just talk to him for the next 15 minutes? There will be a microphone running around. If you're upstairs, there is a microphone stand there. We want to be able to hear you. I see people fleeing. No one's brave enough to ask? My first question...
Two options, unclear or very clear?
Did it make any sense? So what have been some of the most unexpected spin-offs? You've shown us a lot. Were you truly shocked by any spin-offs from this kind of research?
Yeah, there are, but the problem, as I mentioned, if you go to visible, you need the structures with very small, fine structure. And cost of that, for example, one of the samples we are working with is a few $1,000s. You understand that nobody will actually buy it. Even we say that we've created perfect cloak, nobody needs it because we need a kind of commercial type of development. Object much, much smaller. But now imagine that we cover the entire plane, some kind of structures, and you will not see it at all. That's the possibility of developments.
Well, has it already
radio waves? That's probably already done.
Aha, we have a brave soul.
Thanks for your lecture. Your answer to that leads into my question. 15 years since you got started, when does 3D any wavelength happen? Another 15 years or 150? Or 15 months?
Now, you should understand that 15 years people are not working on one device and one concept. Obviously, there are many electric structures with almost no losses. So this means that we did not waste 15 years. We were working for next breakthrough. So previous breakthrough were not that practical in terms of creating particular devices. But it's now, with maybe a few years, this new concept appears, people demonstrate efficiency. For example, in particular, my group, very recent work was on creating of metasurfaces with 99.9 transmission, which will be functional.
Invisibility, then someone standing inside the cloaking device wouldn't be able to see out?
That's a good question, but we don't have 100% visibility. Obviously, this even theoretical cloaks, I mean, in mathematics, this is a kind of conformal transformation, but they are singular transformation. So this border is basically singularity. You don't see outside world. But in reality, of course, this is not infinite, so it's restricted field to penetrate, so it's a ideal and non-ideal, it's a different concept. So.
It's three-dimensional, the holy grail of this at the moment? Is that the...
As far as I understand, nobody working hard on that.
Really?
Nobody wants Harry Potter's magic.
Is it because it's too hard or it's just not relevant?
It's not clear what for.
That shouldn't stop science, should it?
But no. But as I said, that I see the breakthrough in making a one layer, like metasurfaces, covering, varying one layer. That's cool. It will be one layer, so 2D, but you can do it with 3D by just wrapping around. That's probably
solved.
direction. Not yet, not yet.
That's close to solved. I'll just write the headline now, 3D solved
Not
at the
yet,
Academy.
but it's very close.
Hi, yeah, great lecture. I was just wondering, is it possible, if you do theoretically get this, is there any way to actually detect anything inside an invisibility cloak?
What
Is there any way to detect what's inside?
kind of elements which you can create replacing bulky optics? But there are many different type of activities. People try to use it for telecom, but again, before it was not much useful because of losses. With medical applications, metamaterial-based sensors, also that type of activities also exist here. But up to now, the main issue was losses because of the use of many metallic elements inside.
Down here.
Thank you.
Is there a hint there?
Yeah. No, but of course he demonstrated the first metamaterial. What do you expect from him? But in terms of knowledge and understanding, I think everything we already have. Yeah. Conceptual basis is already there. We understand what it should be. It's not liquid inside. It should be kind of dress, and it should bend light. So it should actually make light non-absorbing, non-reflected, but full-time transmitted. Maybe we can do it with our metasurfaces, but we did not try yet.
Next one.
Thank you. I failed physics, so I'm not sure if this question is going to make any sense. But I was just wondering, given that information can be transmitted through waves, could you use a device like this to make data invisible? To make information, to block
what?
it? To make
Data or information invisible.
that is transmitted through waves, for example.
Interesting. I didn't think about that. And I'm not aware. It's a good question. We may start from. No, I'm not aware of that, and it's an interesting angle. Yeah. No, I just wanted to say that metamaterial concept is much more general for than if earthquake coming, it may also bend and make this region completely protected. It's not electromagnetic waves, but it's also part of that concept. So it's general concept for any type of wave phenomena. When waves interact with matter, whatever waves are, heat waves, seismology type of waves, or acoustic waves, or acoustic cloaks demonstrated. And as I mentioned, there is a big project funded by French companies to actually come to the concept of this earthquake-protected region.
Question right up the back.
Yuri, the stealth bomber didn't require metamaterials, but on angles of the surface of the plane to achieve a very low radar signature. Is there a thinking in future terms of an aircraft that will achieve an even lower radar signature?
As I mentioned, the current technology, what we do, because of the sharp angle, so stealth aircraft, like fighters, they scatter in a different way. So the reflected picture received by radars does not correspond to real sizes. For example, it's a reflect from plane, but you see like a duck, swan, that size, That's what current technologies can do. Again, for any type of waves, there are some restrictions. But again, we are not working on that, We are not working on invisibility. For us, invisibility came like a kind of, fun or kind of joke, but it's taken by media so strongly that basically we believe that we are day and night, we are working to make ourselves invisible.
Which means this question better not be about invisibility.
Well, let's let this question be about visibility then. I want to explore this issue of invisibility of all wavelengths. Given the breadth of the electromagnetic spectrum, presumably concept of invisibility of all wavelengths is not really on at all. What is the sort of the spectral range that you expect might be feasible for these types?
For mid-infrared spectrum, but of course not entirely very broadband. And again, it depends on angle, and it depends on, because it's planar type of structure. So there are a lot of limitations. So there is no single solution. As I mentioned, three-dimensional cloaking, conceptually we understand what should be and how it may work, but how to realize it, we don't know, because majority of clocks realized now are two-dimensional, because it related to planar technology of fabrication of nanostructures or nanophotonics. In the metamaterials type of devices, of course, you can always build something around three-dimensional for single wavelength, but again, it's an issue of efficiency and very big losses. You are dealing with microwaves.
Okay. I wasn't sure from the description whether the metamaterials perform their activity, which was shown in a passive way, or was it needing some activation, some energy input in order to perform it? And second, if it's not fully showing transparency, then some energy is being lost. Then it's probably converted to different kind of energy, maybe some heat or whatever. And I wonder if the information being lost on one side is then actually exposed in a different frequency or in a different form.
It's a very complex question, so I answer for the first one. Of course, people are thinking about tunable and active metamaterials. We just published, end of last year, a book of collected chapters, which called Tunable, Active, and Non-Linear Metamaterials. So that's happening, but I just was not able to explain it. And of course, there are active, there are some gain, compensation of losses, there is kind of transformation, so illusion type making devices when you, for example, try to hide person and get a dog visible. A lot of things like that can be done, because what is important that we can engineer the optical space, and even new term appears, transformation optics. So we engineer space, but it may be engineered with passive elements, with active elements, a lot of possibilities, but we can change local properties to make macroscopic properties, desired macroscopic properties. It's a big field and a lot of directions. So basically, it covers a lot of different topics, which simply not possible to present in half an hour, particularly if organizers are driven by invisibility.
We're running out of time with one non-invisibility question here.
Hello. Thank you for the presentation. My question concerns electromagnetic radiation in the microwave and radio frequencies. I had the opportunity once to have a look at a number of antenna designs a long time ago, and they're often very messy and inefficient. And with antenna designs, all sorts of things that are important, like cost and size. And as the wavelengths get longer, the antennas get bigger and bulky and awkward. I was wondering if you could use the mathematics and the knowledge that you have learnt in this in your background to bend wavelengths of light in that frequency to improve the antenna efficiency or design them for specific purposes so you could wrap them around a building instead of hanging them off wherever you...
And in radio physics antennas, particular design of some antennas, if you work on antennas, you should recognize its names like mushroom antennas or reflector array antennas. These are kind of simplified version of metamaterials. And of course, knowledge of metamaterials may improve design of the structures. And this is exactly what one of the companies supported by Bill Gates doing. But unfortunately, I have no idea what they're doing because everything is secret now. But definitely, initial works on improving antenna design were very, very promising. But now they completely washed out from literature.
I know there are a few more questions, but unfortunately we've come up against a deadline, the end of the evening, so we may have to harass Yuri on the way out with very simple questions. But can we please thank Yuri one more time for a very interesting presentation.
Thanks for your interest.